And welcome back. So this time, we will be analyzing this another situation, another scenario, and this time we have an initial condition with the block that is being that we apply the force to the right, and it's initially moving at a velocity of negative v. So it means it's moving to the left, and then a force F is applied to the right, causing the block to have a final velocity or condition that is equivalent to zero, and that is stop moving. So moving from the left and then suddenly it stopped. Okay. So question is, what is the acceleration along the x-axis? So it's moving along the x-axis, and there's no mention that it's moving along the y-axis, and there isn't any condition. There's no other force that you've noticed that would cause it to go upward or downward, or to change its position, change the state of motion along the y-axis. So we can still say that there is no change in motion along the y-axis. There is only a change in motion along the x-axis, as it is being asked, or this is what we're supposed to be looking for. Then F, or the amount of force that is applied to cause it to stop. So again, first condition is for us to write what is it that we know and what are some of the conditions that we must establish. So earlier we said that there is a change in velocity along the x-axis. There isn't any mention about changes in motion along the y-axis, so we can make the assumption that there isn't any changes, and by looking at the illustration, it does make common sense that it's not going to move along the y-axis or change motion along the y-axis. So with those said, we can say that our acceleration along the y-axis is still going to be considered zero, since there's no change in motion. Now, along the x-axis, there is a change in motion. I will call this one as A. So letter A, that represents acceleration. But we have zero, okay? So initial velocity of negative v, okay, and zero. So what is our acceleration? What will be our acceleration? So you might say, well, it's moving to the left, and then suddenly it moves, and then you apply the force, and then it has zero. So should it be positive acceleration, or should it be negative acceleration? Some of you might immediately say, well, it's slowing down. It is slowing down. Yes, I agree with you, it's slowing down, so the acceleration should be negative. But in this case, it should be positive, because the motion is going to the left, therefore the acceleration is the opposite direction of a negative velocity in order to attain what we call at rest, or to stop or change the motion. So therefore we can say that your acceleration right here should be positive in order to get from negative to zero. In order to get from negative to zero, we must have an acceleration that is positive, that is opposite the direction of our velocity. So let us see if this will show up as we have made the um, assumption that it's positive. So next step, as always, we have to start with our free body diagram. And by looking at the free body diagram, okay, before we start a free body diagram, let's draw our imaginary x and y coordinates in our block, where the intersection is considered as your point of origin. So let me just write it down, free body diagram, or FBD. So here's our FBD, free body diagram. So again, let's draw the dot. There's no change, okay, there's no change along the y-axis. So all forces along the y-axis should be the same length, or should have the same magnitude. So the first force that we all know that exists is force due to gravity, or our weight, which is dependent on the mass. Second is our normal force. Since it is along the floor or along the table or along a flat surface, so therefore we have our normal force. Now we have our force acting this direction. So acting this direction, maybe I'll just put force over here. So force of gravity, force, not force of gravity, but the applied force. And maybe there is another force, which is dependent on our mu. Mu means the coefficient of friction. Since it's moving, so therefore it is the kinetic friction. And since the motion is going to the left, velocity is going to the left, so therefore our force of friction should always be opposite the direction of our motion. So I would say maybe this is our force of friction. So this is our force of friction, and that force of friction will definitely be your kinetic friction, FFK. Okay, again, the reason why it's pointing to the right, because this time it's moving to the left. So it's kinetic friction causing it to slow down also. So kinetic friction, and we have our applied force. So it means that the kinetic friction wasn't strong enough to stop the object. So what causes it to stop the object is a combination of both the kinetic friction and our applied force. Now, let us write the relationships that we know. Fg is mass times the gravitational field strength or acceleration due to gravity, depending on which one do you want to use, but it does provide us with the same response mathematically. And then we have our force of friction. This time it's kinetic, so therefore we are using our kinetic friction, coefficient of friction, multiplied by the normal force Fn. Okay, so normal force Fn. Let us continue. Okay, so now we have everything set up over here. Now let us continue. Again, you might say, well, you keep on repeating these forces along the y-axis, knowing that there's no change in state of motion. But it is much better that we write it all the time, so it's more of like a muscle memory that we know what we're doing. So we keep on repeating. So mass multiplied by the acceleration along the y-axis. Let's analyze the forces acting along the y-axis. Positive going up, negative going down. So we have positive normal force minus our Fg, which is force of gravity. That is your mass multiplied by 0, as it says over here. Now we can further say that Fn minus Fg is simply equivalent to 0. And our Fn is equal to Fg, or Fn is automatically, or let's just write it down that it's mg. Normal force is also equivalent to your mass times g. Now, let us move on to the next step, and that is to analyze the forces acting on the y-axis, x-axis. So at this point, it's a little bit, how do I describe it? It's a little bit different compared to what we've been doing in the past. So this time, the summation of forces acting along the x-axis is mass multiplied by the acceleration along the x-axis. This time, the acceleration along the x-axis is not 0, so it will not be equivalent to 0. So the forces shouldn't be equivalent to 0. The difference between those forces shouldn't be equivalent to 0. This time, we don't have forces acting along the x-axis. We have forces acting along the x-axis, but nothing pointing to the left. So we can say, that if forces going to the right, forces going to the right is positive. So we can say that force, applied force, plus force of friction or kinetic friction is equivalent to mass multiplied by the acceleration A. Acceleration A. So now, if we want to figure out the acceleration using this basic equation, we know that our acceleration is force plus force of friction kinetic divided by m. So you divide both sides by the mass and we get our acceleration. And look, it's positive acceleration, just like what we made the assumption earlier. It should be positive acceleration. Now we can further reduce this or simplify this by replacing the value of force of friction, which is the coefficient of kinetic friction multiplied by the normal force, and we all know that the normal force is mg. You know what, let me just put the step-by-step process so that you don't skip anything. So now our acceleration is equivalent to F plus mu k mass times g divided by mass. This time, okay, if I'm going to simplify this, I will not make the same mistake as I did in the previous video. So this time I have F over m plus, okay, mu k times g. In the previous video, we didn't have plus mu k times g, but instead it's minus, okay? It was minus. This time we have to add because we are going against the direction of the block. So the force is applied opposite, so we need to get a positive acceleration because the direction of velocity is negative and to the left. In order to get to zero, the acceleration should be on the opposite direction. Now, just like what we did in the previous section, let us use this side of the equation. Let's use this form in our equation. So let's write it down. F plus Fk equals mass times acceleration. This time we want to figure out how much force do we need. Okay, how much force do we need in order to attain that acceleration? So we need to move this force of friction to the other side of the equation to make sure that we have force, the applied force by itself, okay, mathematically to represent our answer. So now we have F is equivalent to mass times the acceleration minus force of friction or kinetic force of friction. F. So now let's simplify it by changing the force of kinetic friction into the equivalent kinetic friction, which is mu k times Fn, or we can just go straight to our mass times g. So that is ma minus mu k times mass times g. In the previous previous scenario, we did solve for it, but it was positive mu k, or a coefficient of kinetic friction multiplied by mass, and the acceleration due to gravity or gravitational field strength, whatever you want to use, it's the value of g. So F is m, so let's factor out m. That will give us a minus mu k times g. So this will be the amount of force needed, and this is our answer for letter B. And this is our answer for letter A. So this is letter A. Let me just put it here, letter A. And this is letter B. Hope you like our video today, and you're getting used to it and getting familiar with the process. I'll see you in the next video with a different scenario.